95% of everything that exists cannot be touched, cannot be photographed, cannot even reflect light, and yet without it, every galaxy would fly apart like water flung from a spinning wheel. There is a kind of matter woven through the cosmos that holds stars in their slow rotations, that keeps clusters of galaxies from drifting into the void, and no instrument has ever captured a single particle of it. This is the story of what we cannot see, and how we know it must be there, shaping the darkness between all things. If these quiet explorations help carry you toward rest, a subscription means more nights like this one, whenever sleep feels far away. The universe, it turns out, is mostly hidden, and that hidden architecture is where we begin. If you were to step outside on a clear night, far from the glow of street lamps and the ambient light of cities, and if you were to tilt your head back and let your eyes adjust to the darkness for several minutes, you would begin to see what countless generations of humans have seen before you. The stars would emerge slowly at first, the brightest ones appearing almost immediately, and then, gradually, as your pupils widened and the cells at the back of your eyes became more sensitive, fainter and fainter points of light would reveal themselves until the entire dome of the sky seemed scattered with tiny, luminous grains. This is the view that has accompanied humanity for as long as we have existed. The same essential canopy that our ancestors contemplated while sitting around fires on ancient savannas. The same scattered brilliance that shepherds watched while tending their flocks through long quiet nights. The same patient sprinkling of light that sailors used to find their way across featureless oceans. On such a night, if you were patient and the conditions were favorable and your eyes were reasonably keen, you could count approximately 6,000 stars visible to the unaided human eye. This number might seem surprisingly small when you consider how vast the sky appears, or it might seem impressively large when you imagine actually attempting to count them one by one. Either way, this figure of roughly 6,000 represents the entirety of stellar light that reaches us with sufficient brightness for our biological eyes to detect without assistance. Half of these stars would be below the horizon at any given moment, of course. So from any single location you might see perhaps 3,000 at once, though the exact number varies depending on your latitude and the clarity of the atmosphere and how long you allow your eyes to adapt to the darkness. For most of human history, these several thousand points of light constituted the complete stellar inventory of the universe as far as anyone could determine. The ancient Babylonians watched them and recorded their positions on clay tablets. The Egyptians aligned their monuments with particular stars and tracked their movements across the seasons. Indigenous peoples around the world developed their own rich traditions of stellar observation, mapping not only individual stars but also the dark spaces between them, finding meaning and utility in patterns that had remained fixed for countless generations. The stars were dependable, eternal, and seemingly countable. Among the many careful observers of antiquity, one figure stands out for the systematic rigor of his approach: Hipparchus of Nicaea. Working around 129 BCE on the island of Rhodes, undertook the painstaking task of creating what is generally considered the first comprehensive star catalogue in the Western astronomical tradition. Over many nights of careful observation, Hipparchus recorded the positions of approximately 850 stars, noting their locations against the celestial sphere and organizing them according to their apparent brightness. He divided the stars into 6 categories of magnitude, with the first magnitude containing the very brightest stars visible, and the 6th magnitude containing those that hovered just at the edge of visibility. This system of magnitudes, though refined and extended many times since, still forms the basis of how astronomers describe stellar brightness today, a quiet testament to the enduring value of careful observation. The catalogue of Hipparchus represented a kind of census of the visible cosmos, an inventory of luminous objects that seemed to account for everything significant in the heavens beyond the wandering planets and the moon. Later, astronomers would refine and expand upon his work, most notably Claudius Ptolemy, whose own star catalogue from the 2nd century CE formed the standard reference for more than 1,000 years. But the fundamental assumption remained unchanged across all these centuries of observation. The stars that could be seen were the stars that existed. The visible universe was the complete universe. What met the eye was what there was to find. This comfortable assumption persisted until the early 17th century, when a mathematics professor in Padua turned a newly invented optical device toward the night sky and discovered that the universe was far more populated than anyone had imagined. Galileo Galilei, in the winter of 1609 and 1610, used his improved telescope to observe the heavens with unprecedented clarity. And among his many startling discoveries was the revelation that the Milky Way, that soft glowing band stretching across the sky, was not a continuous luminous cloud as it appeared to the naked eye, but rather consisted of countless individual stars, too faint and too densely packed to be resolved without optical aid. Where ancient observers had seen a misty river of light, Galileo saw stars beyond counting, each one a distinct point of illumination that had simply been too dim for human eyes to perceive on their own. The 6,000 stars visible without a telescope suddenly represented only the nearest and brightest members of a vastly larger population. The universe had grown enormously in a single season of observation, and yet this expansion brought no particular anxiety, only a sense of wonder at the richness of creation. There were simply more of the same things that had always been there. More stars, more points of light, more luminous matter scattered across a space that now seemed considerably more extensive than previously understood. As telescopes improved over the following centuries, the stellar census continued to expand. Larger mirrors and better lenses revealed fainter and fainter stars, each improvement in technology bringing new populations of distant suns into view. By the late 18th century, William Herschel, a German-born musician who had become one of the most dedicated astronomical observers in history, attempted to determine the actual shape and extent of the stellar system by the straightforward method of counting stars in different directions. Herschel's approach was admirably direct. If stars were distributed more or less uniformly through space, then the number of stars visible in any particular direction should tell you something about how far the stellar system extended in that direction. More stars meant greater depth. Fewer stars meant you were looking toward the edge of the distribution. Working with his sister Caroline, who served as his invaluable assistant and record keeper, Herschel counted stars in hundreds of sample regions scattered across the sky, tabulating their numbers with careful precision. The result of this stellar census, published in 1785, suggested that the Milky Way was a flattened disk of stars, considerably wider than it was thick, with the Sun located somewhere within this vast assemblage. Herschel's model was not entirely accurate, as he had no way of knowing that dust clouds within the galaxy obscured many distant stars and distorted his counts. But his basic insight was sound. The stars were not scattered randomly through infinite space, but rather collected into a definite structure with a particular shape, an island of light floating in the cosmic darkness. Throughout the 19th century, astronomers continued to refine this picture, mapping the galaxy with increasing precision and cataloguing ever larger numbers of individual stars. Photographic plates replaced the human eye as the primary recording device, allowing much longer exposures that could capture light too faint for any observer to see directly. The stellar population climbed into the millions, then into the hundreds of millions, and still the fundamental assumption held. The universe consisted of luminous matter, stars and the gas from which they formed, and the glowing nebulae in which new stars were being born. Everything that existed gave off light, and everything that gave off light could eventually be detected and counted and added to the grand inventory. There were, admittedly, some puzzling objects that did not fit neatly into this picture. Scattered across the sky were fuzzy patches of light called spiral nebulae, which showed a distinctive pinwheel structure when observed through sufficiently powerful telescopes. Some astronomers believed these were nearby gas clouds, perhaps solar systems in the process of formation. Others suspected they might be distant collections of stars, separate island universes lying far beyond the boundaries of the Milky Way. The question remained unresolved for decades, a matter of ongoing debate but not particular urgency. The answer came definitively in the 1920s through the work of Edwin Hubble at the Mount Wilson Observatory in the mountains above Los Angeles. Using the 100-inch Hooker telescope, then the largest in the world, Hubble was able to resolve individual stars within the Andromeda Nebula, one of the brightest and most prominent of the spiral objects. Among these stars, he identified a particular type called Cepheid variables, whose intrinsic brightness was already well understood from studies of similar stars within our own galaxy. By comparing the known luminosity of these Cepheid variables with their observed faintness, Hubble could calculate their distance, and the result was remarkable. The Andromeda Nebula lay far outside the Milky Way, nearly 1 million light-years distant by his initial estimate, which was later revised upward to more than 2 million light-years. It was not a gas cloud or a forming solar system, but rather an entirely separate galaxy, a vast collection of hundreds of billions of stars, comparable in size to our own Milky Way and separated from us by an almost incomprehensible gulf of empty space. The universe had expanded once again, even more dramatically than it had in Galileo's time. Where there had been one galaxy, there were now at least two, and as astronomers turned their attention to other spiral nebulae, they found that nearly all of them lay at similarly enormous distances. The universe was filled with galaxies, millions and eventually billions of them, each containing its own population of stars, each separated from its neighbors by vast reaches of nearly empty space. And yet, even as this expansion transformed human understanding of cosmic scale, the fundamental assumption about the nature of the universe remained intact. Galaxies were made of stars. Stars were made of luminous matter. The universe, however vast it might prove to be, consisted essentially of things that gave off light. The visible cosmos was the real cosmos. What telescopes revealed was what existed. There might be more of it than anyone had previously suspected, stretching across distances that strained the imagination. But it was all fundamentally the same kind of stuff. Ordinary matter radiating ordinary light across ordinary space. This was a deeply satisfying picture, and it seemed complete. The universe was enormous but comprehensible. It was made of familiar ingredients arranged in orderly structures. Stars gathered into galaxies. Galaxies gathered into clusters, and all of it glowed with the reassuring light of nuclear fusion and gravitational collapse, and the ordinary physical processes that textbooks described so well. Astronomers had spent centuries cataloguing this luminous matter, from the 850 stars of Hipparchus to the hundreds of billions of galaxies revealed by modern surveys. And at each step the inventory had grown, but the basic accounting had remained balanced. The light told you where the matter was. The matter produced the light. Everything visible, everything accounted for. This orderly picture would eventually prove to be incomplete in a very profound way. But that revelation lay in the future. For now, for many comfortable decades, the universe seemed to be exactly what it appeared to be. A vast but ultimately knowable collection of luminous objects scattered across space, inviting patient study and careful cataloguing, giving up its secrets to anyone with sufficient time and sufficiently powerful instruments. The sky was full of light, and the light seemed to tell the whole story. In the early 1930s, in the dry hills above Pasadena, where the California Institute of Technology spread its low buildings beneath an often cloudless sky, there worked a Swiss astronomer whose name would one day be attached to one of the greatest mysteries in all of science. Though during his lifetime he received rather less recognition than his discoveries perhaps deserved. Fritz Zwicky had arrived at Caltech in 1925, brought over from Switzerland to work on the physics of crystals. But he soon found his attention drawn upward, away from the orderly lattices of atoms in solid matter, and toward the far stranger arrangements of matter scattered across the cosmos. The great gatherings of galaxies that populate the universe in patterns we are still working to understand. Zwicky was, by all accounts, an unusual man, possessed of a fierce intelligence and an equally fierce temperament, given to bold proclamations and sweeping theoretical ideas that sometimes proved correct and sometimes did not. Though when he was right, he was often spectacularly so. He had little patience for what he perceived as the intellectual timidity of his colleagues, and he made few efforts to soften his opinions or smooth over disagreements, which meant that his relationships with other astronomers were often strained, sometimes irreparably. There is a story, perhaps apocryphal but widely repeated, that his colleagues at Caltech referred to him as a spherical bastard. The joke being that he appeared equally unpleasant no matter which direction you approached him from, like a sphere that presents the same surface at every angle. Whether or not this particular phrase was actually used, the sentiment behind it captures something of the difficult position Zwicky occupied in the astronomical community of his time. Respected for his undeniable brilliance, but often isolated by his abrasive manner and his willingness to make enemies. In 1933, Zwicky turned his attention to a vast collection of galaxies known as the Coma Cluster, which lies approximately 320 million light-years from our own small corner of the universe, in the direction of the constellation Coma Berenices. A galaxy cluster is exactly what its name suggests. A gathering of galaxies held together by their mutual gravitational attraction, much as the stars in a single galaxy are held together, or the planets in a solar system, though the scales involved are almost incomprehensibly larger. The Coma Cluster contains over 1,000 galaxies, each one a vast city of stars, and all of them moving through space in a complex gravitational dance, orbiting around their common center of mass, falling toward one another and swinging past and falling again, bound together across millions of light-years by the invisible threads of gravity. Zwicky wished to understand this cluster, to measure its properties and determine its mass. And to do so, he employed a technique that relies on one of the most useful tools available to astronomers, the phenomenon known as redshift. When a source of light is moving away from an observer, the light it emits is stretched out, its wavelength becoming longer. And since longer wavelengths correspond to the red end of the visible spectrum, this stretching shifts the light toward red, hence the name. The faster an object is moving away, the more its light is shifted, and by measuring this shift precisely, using the characteristic patterns of light absorbed and emitted by different elements, astronomers can determine how fast a distant object is moving with remarkable accuracy. It is a bit like listening to the pitch of a siren as an ambulance passes by, except that instead of sound waves being compressed and stretched, it is light, and instead of measuring the speed of a vehicle on a road, one is measuring the speed of an entire galaxy hurtling through the void. Zwicky measured the redshifts of galaxies in the Coma Cluster, carefully recording how fast each one appeared to be moving relative to the cluster as a whole. And when he compiled his data, he found something deeply puzzling. The galaxies were moving very fast indeed, much faster than he had expected. Their velocities scattered across a surprisingly wide range, some approaching, some receding, all in rapid motion within the cluster. This was not necessarily a problem in itself, since galaxies in a cluster are expected to be in motion, but the speeds Zwicky measured were so high that they presented a serious difficulty when he tried to reconcile them with the amount of matter he could see. The problem can be understood through a simple analogy, though of course the reality is rather more complicated. Imagine a group of dancers holding hands and spinning in a circle, their linked arms providing the force that keeps them together as they whirl around their common center. If the dancers spin slowly, a gentle grip is sufficient to maintain the circle, but if they spin faster, they must hold on more tightly, and if they spin faster still, even the strongest grip will eventually fail and the dancers will fly apart, flung outward by their own momentum. The galaxies in a cluster are like those dancers, except that instead of linked hands, they are held together by gravity, and the strength of that gravitational grip depends on the total mass of the cluster. More mass means more gravity, which means the cluster can hold on to faster-moving galaxies without flying apart, while less mass means a weaker grip, and galaxies cannot be moving too quickly or the cluster will disperse. When Zwicky calculated how much mass the Coma cluster would need to hold itself together, given the velocities he had measured, he arrived at a number that was startlingly large, far larger than the mass he could account for by adding up all the visible light from all the galaxies in the cluster and estimating how many stars that light represented. The discrepancy was not small, not a matter of being off by a factor of 2 or 3, which might have been attributed to measurement uncertainties or to some error in his calculations. Instead, Zwicky found that the cluster appeared to contain roughly 400 times more mass than he could see, a factor so large that it could not be easily dismissed, and yet so unexpected that it seemed to demand some explanation beyond ordinary stars and gas. Zwicky, being Zwicky, was not shy about proposing such an explanation. He suggested that the cluster must contain a vast amount of matter that was invisible to telescopes, matter that exerted gravitational pull but did not emit or reflect light in any detectable amount, and he gave this hypothetical substance a name, calling it Dunkel Materie, which is simply the German phrase for dark matter. It was a straightforward term, descriptive rather than evocative, a label for something whose nature was entirely unknown, but whose presence seemed, to Zwicky at least, to be required by the evidence. The matter was dark because it could not be seen, and it was matter because it had mass and exerted gravity. And beyond those two facts, Zwicky could say nothing about what it might actually be. One might expect that such a dramatic claim, backed by careful observations and sound reasoning, would have captured the attention of the astronomical community and sparked an intensive effort to understand this mysterious invisible substance. But in fact, the opposite occurred. Zwicky's findings were largely ignored, filed away as an interesting curiosity, but not pursued with any urgency. And for several decades, the question of the missing mass in galaxy clusters remained a backwater of astronomical research, occasionally mentioned but seldom investigated in depth. There are several reasons why this happened, and Zwicky's difficult personality was certainly one of them. Scientists are human beings, and human beings are more inclined to take seriously the ideas of colleagues they like and respect than the ideas of colleagues who have insulted them or belittled their work, even when the ideas themselves are perfectly sound. Zwicky had made many enemies over the years, and his manner of presenting his findings, often with an air of superiority and disdain for those who failed to grasp their significance, did little to encourage others to follow up on his work. This is not a flattering portrait of how science operates, but it is an honest one, and it helps to explain why a discovery that should have revolutionized our understanding of the universe instead languished in relative obscurity for the better part of 40 years. There were also legitimate scientific concerns about Zwicky's conclusions. His sample of galaxies was relatively small, and his measurements, while careful, were subject to various uncertainties that made it difficult to be certain just how fast the galaxies were really moving. The estimates of visible mass were also uncertain, depending, as they did, on assumptions about how much light a typical star produces and how many stars a given galaxy might contain. Assumptions that were less well constrained in 1933 than they would become in later decades. It was possible, some argued, that the discrepancy Zwicky had found was simply the result of errors in his measurements or flaws in his assumptions, and that more careful work with better instruments would eventually make the missing mass disappear. And yet, Zwicky was not entirely alone in suspecting that something was amiss with our accounting of the mass in the universe. Just 1 year earlier, in 1932, the Dutch astronomer Jan Oort had published observations suggesting a similar discrepancy, though on a somewhat smaller scale and in a different context. Oort had been studying the motions of stars in the disk of our own Milky Way galaxy, particularly stars located near the galactic plane, that flattened region where most of the galaxy's stars and gas are concentrated. By measuring how fast these stars moved up and down relative to the plane, oscillating gently as they orbited the galactic center, Oort could estimate the total amount of mass in the disk, since more mass would produce a stronger gravitational pull and faster oscillations. What Oort found was that the stars appeared to be moving faster than they should, given the amount of visible matter in their neighborhood, suggesting that there was additional mass present, mass that was not accounted for by the stars and gas that could be directly observed. The discrepancy was not as dramatic as the one Zwicky would find in the Coma cluster, but it pointed in the same direction, toward the existence of some form of invisible matter that contributed to the gravitational field without contributing to the light we could see. Oort was a more diplomatic figure than Zwicky, well respected in the astronomical community and known for careful, methodical work. But even so, his findings did not spark immediate concern. The missing mass he had detected might, after all, be explained by faint stars too dim to be easily counted, or by cold gas that did not emit much light, or by various other forms of ordinary matter that simply happened to be difficult to observe. There was no pressing need to invoke anything exotic, and so the astronomical community largely shrugged and moved on, noting the discrepancy but not worrying over much about what it might mean. And so the first whispers of dark matter faded into the background noise of astronomical research, heard but not heeded, recorded in the scientific literature but not followed up with the intensity they perhaps deserved. Zwicky went on to make other important contributions to astronomy, including foundational work on supernovae and neutron stars, while Oort continued his meticulous studies of galactic structure, and the question of the missing mass was left to simmer quietly, waiting for a later generation of astronomers to take it up again and pursue it to its strange and still unfinished conclusion. The universe, as it turned out, was in no hurry to reveal its secrets. It had kept the existence of dark matter hidden from us for billions of years, and it could afford to wait a few decades more, while humanity slowly gathered the tools and the evidence and the willingness to accept what the data were telling us, that most of the matter in the cosmos is invisible, that the stars and galaxies we see are only a small fraction of what is really there, that we are surrounded by something vast and dark and utterly unlike anything we have ever encountered on Earth. But all of that lay in the future, decades away, and for now the early whispers went unheeded, and the universe kept its secret a little longer. In the year 1948, a young woman named Vera Rubin applied to the graduate astronomy program at Princeton University, and she received in reply a letter explaining that women were simply not permitted to enroll in that department. that the observatory and its facilities were reserved for men, and that she would need to look elsewhere if she wished to continue her studies of the stars. This was not an unusual circumstance for the time, and Vera Rubin did look elsewhere, eventually completing her doctoral work at Georgetown University while raising her children and commuting to classes in the evenings. And she would go on to make one of the most important astronomical discoveries of the 20th century, a discovery that revealed how little we truly understand about the composition of the universe and how much of reality remains hidden from our direct observation. Vera Rubin had been fascinated by galaxies since her childhood in Washington, D.C., where she would lie awake watching the stars wheel past her bedroom window. And this fascination never left her even as she encountered obstacle after obstacle in her pursuit of astronomical knowledge. After Princeton's rejection, she earned her master's degree at Cornell University, where she wrote a thesis suggesting that galaxies might be clustered together and moving in coordinated streams rather than distributed randomly throughout the cosmos, an idea that was considered peculiar at the time but would later prove to be essentially correct. She then moved to Georgetown for her doctorate, studying under George Gamow, and her dissertation examined whether galaxies were distributed evenly throughout space or whether they tended to clump together in certain regions. Another question that touched upon the large-scale structure of the universe that would occupy astronomers for decades to come. By the 1960s, Vera Rubin had joined the staff of the Carnegie Institution of Washington, which was one of the few major research facilities at the time that welcomed women scientists. And it was there that she began a collaboration with an instrument maker named Kent Ford that would change our understanding of the cosmos. Kent Ford had designed and built a remarkably sensitive device called an image tube spectrograph, which could measure the light from distant astronomical objects with unprecedented precision, breaking that light into its component wavelengths and allowing astronomers to determine how fast those objects were moving towards or away from the observer through the Doppler shift of their spectral lines. The spectrograph was a delicate and temperamental instrument, requiring careful calibration and patient observation, but in the hands of Ford and Rubin, it became a tool for uncovering one of nature's deepest secrets. The project that Rubin and Ford undertook together in the 1970s seemed straightforward enough at first glance, for they simply wished to measure how fast different parts of spiral galaxies were rotating, mapping the orbital velocities of stars and gas clouds at various distances from the galactic center. This kind of measurement had been attempted before with less sensitive equipment, and astronomers had certain expectations about what the results should show. Expectations based on our understanding of gravity and orbital mechanics as they had been developed over centuries of careful observation and mathematical analysis. The prevailing assumption was that galaxies should behave rather like our own solar system, with objects near the center orbiting quickly and objects farther out orbiting more slowly, because this is what happens when most of the mass is concentrated in one central location. To understand why astronomers expected this pattern, it helps to consider how the planets in our solar system move around the Sun. Mercury, the innermost planet, completes an orbit in just 88 days, racing around the Sun at a tremendous velocity, while Neptune, far out in the cold outer reaches of the system, takes 165 Earth years to complete a single circuit, moving at a comparatively leisurely pace through the darkness. This relationship between distance and orbital speed is a direct consequence of how gravity works. For objects closer to a central mass feel a stronger gravitational pull and must move faster to avoid falling inward, while objects farther away feel a weaker pull and can maintain their orbits at lower velocities. The mathematical expression of this relationship is called Keplerian dynamics, after Johannes Kepler, who first described the laws governing planetary motion in the early 17th century. And when astronomers plot orbital velocity against distance from the center on a graph, they expect to see a curve that rises sharply near the center and then declines steadily as one moves outward, falling off in a characteristic pattern that reflects the concentration of mass in the middle of the system. The first galaxy that Rubin and Ford studied in detail was Andromeda, also known by its catalogue designation M31, which is the nearest large spiral galaxy to our own Milky Way and has been observed by astronomers for centuries. Andromeda is visible to the naked eye on dark nights as a faint smudge of light in the constellation that bears its name, and through a telescope it reveals itself as a magnificent pinwheel of hundreds of billions of stars, with graceful spiral arms winding outward from a bright central bulge. Because of its relative proximity, only about 2.5 million light-years away, Andromeda provides an excellent laboratory for studying galactic structure and dynamics, and Rubin and Ford pointed their spectrograph at various regions of this galaxy, measuring the velocities of stars and gas clouds from the bright center out to the faint, sparse edges where the visible matter trails off into the darkness of intergalactic space. The measurements that emerged from their observations were puzzling, for they did not match the expected pattern at all. Near the center of Andromeda, the rotation velocities were indeed quite high, which was not surprising given the concentration of stars and presumably mass in that region. But as Rubin and Ford measured points farther and farther from the center, moving out along the spiral arms toward the dim outer reaches of the galaxy, the velocities did not decline as Keplerian dynamics predicted they should, and intense. The orbital speeds remained essentially constant, with stars and gas clouds at the very edge of the visible galaxy, moving just as fast as those much closer to the center. When they plotted their data on a graph, the rotation curve did not fall off in the expected manner, but remained flat, stretching out in a horizontal line that seemed to defy the laws of gravity as they were understood. At first, Rubin and Ford considered whether there might be some error in their measurements, some systematic problem with the spectrograph or their observations that was producing spurious results. But they checked and rechecked their work and found no mistakes. They then turned their attention to other spiral galaxies, reasoning that if Andromeda was somehow unusual, other galaxies might show the expected declining rotation curves. Over the following years, they observed more than 60 spiral galaxies of various sizes and orientations, measuring rotation velocities with painstaking care, and in every single case they found the same anomaly. Every galaxy showed a flat rotation curve, with outer regions spinning far too quickly to be explained by the gravitational pull of the visible matter alone. The consistency of this result across so many different galaxies made it clear that this was not a peculiarity of Andromeda, but a universal feature of spiral galaxies everywhere. The implications of these flat rotation curves were profound and unsettling. For they suggested that our inventory of the matter in galaxies was dramatically incomplete. If the visible stars, gas clouds, and dust were the only sources of gravity in a galaxy, then the outer regions should indeed be moving slowly, following the Keplerian pattern that works so well for explaining planetary orbits. The fact that they were moving so fast meant that there must be additional matter present, matter that was exerting gravitational pull and keeping those outer stars in their rapid orbits. But matter that was completely invisible to our telescopes and instruments. This invisible matter, whatever it might be, would have to be distributed in a vast spherical halo surrounding each galaxy, extending far beyond the visible edges of the stellar disk, because only such a distribution could produce the flat rotation curves that Rubin and Ford were observing. Vera Rubin described this situation with characteristic clarity when she remarked that what you see in a spiral galaxy is not what you get, meaning that the luminous matter visible through our telescopes represents only a small fraction of the total mass present. The stars and gas that we can observe are, in a sense, merely floating on the surface of a much larger and completely invisible structure, like leaves on the surface of a dark pond whose depths we cannot see. The galaxy that appears in our photographs and images is not the whole galaxy, but only its most conspicuous component. And the true extent of galactic matter stretches out into regions where no light shines and no stars burn. When Rubin first presented these findings to the astronomical community, the response was mixed, with many researchers expressing skepticism about such a dramatic claim. Some suggested that might be errors in the measurements despite Rubin's careful work, while others proposed that perhaps our understanding of gravity needed to be modified at galactic scales, that Newton's laws might not apply in quite the same way when dealing with systems as large as galaxies. But as more observations accumulated from Rubin and Ford and from other astronomers who began to investigate the same questions, the evidence became overwhelming. Galaxy after galaxy showed the same flat rotation curves, the same indication of vast amounts of unseen matter. And gradually, the astronomical community came to accept that something extraordinary was going on. The matter that was holding galaxies together came to be called dark matter, a name that reflects our ignorance of its true nature, for we call it dark simply because it does not emit or absorb light, and we call it matter because it exerts gravitational influence like ordinary matter does. The amount of dark matter required to explain the observed rotation curves is substantial, far exceeding the mass of all the visible stars, gas, and dust combined. Current estimates suggest that for every kilogram of ordinary matter in a typical galaxy, there are roughly 5 or 6 kilograms of dark matter, meaning that the luminous galaxies we observe are actually minority components of much larger and more massive dark matter structures. The shape of these dark matter structures, inferred from the rotation curve data and subsequent observations, is that of a roughly spherical halo that envelops the visible galaxy and extends far beyond it in all directions. The visible disk of a spiral galaxy, with its beautiful arms and bright central bulge, sits near the center of this halo like a small, bright object embedded in a much larger invisible cloud. The dark matter halo is not uniform, but rather denser toward the center and more diffuse toward the edges. And its gravitational influence is what keeps the outer stars of the galaxy moving at their unexpectedly high velocities. Without this halo, the outer regions of galaxies would simply fly apart, unable to hold themselves together against the centrifugal forces of their rotation. Vera Rubin continued her work on galaxy dynamics for many decades, becoming one of the most respected astronomers of her generation and receiving numerous honors and awards for her contributions to science. Though the Nobel Prize in Physics eluded her, despite widespread agreement that her work was deserving of such recognition. She remained an advocate for women in science throughout her career, having experienced firsthand the barriers that could be placed in the path of talented researchers simply because of their gender, and she mentored many young scientists who went on to make their own contributions to our understanding of the cosmos. She passed away in December of 2016 at the age of 88, having transformed our picture of the universe from one dominated by luminous matter to one in which most of the mass is hidden from view. The flat rotation curves that Vera Rubin and Kent Ford discovered in the 1970s remain one of the strongest pieces of evidence for the existence of dark matter, and their observations have been confirmed and extended by countless subsequent studies using ever more sophisticated instruments and techniques. We now know that the phenomenon they uncovered is not limited to spiral galaxies, but appears in many different astronomical contexts, from the motions of galaxies within clusters to the gravitational lensing of light by massive structures to the patterns of temperature fluctuations in the cosmic microwave background radiation left over from the early universe. All of these independent lines of evidence point toward the same conclusion, that the universe contains far more matter than we can see, and that this invisible matter plays a crucial role in shaping the cosmos on the largest scales. And so we may rest with the knowledge that galaxies, those magnificent islands of stars scattered throughout the vastness of space, are not quite what they appear to be, that they are embedded in structures far larger and more mysterious than their visible components suggest, and that the matter we can observe represents only a small portion of what is truly there. Light has a way of telling us secrets about places it has traveled through, even when those places appear to hold nothing at all. To understand how we came to know that most of the universe remains hidden from our eyes, we must first consider something that Albert Einstein proposed in the year 1915, when he completed his general theory of relativity and offered humanity an entirely new way of thinking about gravity, space, and time. In his theory, gravity was not a force pulling objects toward one another across empty space, as Isaac Newton had described it centuries earlier, but rather a curvature in the fabric of space and time itself, caused by the presence of mass and energy. Massive objects, Einstein suggested, do not simply attract other objects, but instead bend the very geometry of the space around them, and anything traveling through that curved space, including light itself, must follow the contours of that curvature, much as a marble rolling across a stretched rubber sheet will curve toward any heavy object pressing down upon it. This was a remarkable prediction, and it carried with it an observable consequence that could be tested. If a massive object truly bends the space around it, then light passing near that object should follow a curved path rather than traveling in a perfectly straight line. The effect would be subtle for most objects, but for something as massive as our Sun, the bending should be just measurable enough to detect. if one could observe starlight passing very close to the solar edge. The difficulty, of course, was that the sun's own brilliant light normally drowns out any stars that appear near it in the sky, making such observations impossible under ordinary circumstances. But during a total solar eclipse, when the moon passes directly between the Earth and the sun and blocks out the solar disk, the stars near the sun become briefly visible against the darkened sky, and their positions can be carefully measured and compared to where they appear when the sun is elsewhere. And so it was that in May of 1919, the British astronomer Arthur Stanley Eddington led an expedition to the island of Principe, off the western coast of Africa, to observe a total solar eclipse and test Einstein's prediction. A second team traveled to Sobral, in northern Brazil, to make parallel observations in case clouds obscured the view from one location. The measurements required great precision and great patience, for the apparent shift in stellar positions predicted by general relativity amounted to less than 2 arcseconds, a tiny fraction of a degree. When the results were analyzed and announced later that year, they confirmed that starlight passing near the sun was indeed deflected by approximately the amount Einstein had calculated, not by the smaller amount that a simpler Newtonian calculation might suggest. The curvature of space around a massive object had been observed directly through its effect on light, and Einstein's theory of general relativity gained powerful support. The phenomenon became known as gravitational lensing, because the bending of light by massive objects is somewhat analogous to the way a glass lens bends light passing through it, though the underlying physics is quite different. In the decades that followed, astronomers came to understand that gravitational lensing could serve as a tool for studying the universe itself. If light from a distant galaxy passes near a massive foreground object on its way to our telescopes, that light will be bent and distorted, and sometimes focused in ways that produce multiple images of the same background source, or stretched arcs of light, or even complete rings when the alignment is particularly precise. By studying these distortions, astronomers can learn about the mass and distribution of the foreground object that caused the bending, even if that object is too faint or too diffuse to observe directly. The strength of the lensing effect depends on the total mass enclosed within the light's path, and this includes all forms of matter, whether luminous or dark, whether visible in any wavelength of light, or completely invisible to every telescope ever built. It was through gravitational lensing that some of the most compelling evidence for dark matter eventually emerged. Evidence that went beyond the motions of stars and galaxies and offered instead a direct view of where mass is located in space. One of the most important observations in this regard came from a remarkable cosmic event known as the Bullet Cluster, a system with the formal designation 1E06575588, located approximately 3.8 billion light-years from Earth in the southern constellation Carina. The Bullet Cluster is not a single object, but rather the aftermath of a collision between two large galaxy clusters, collections of hundreds or thousands of galaxies bound together by gravity and embedded within vast halos of hot gas and, as we now know, dark matter. This collision occurred approximately 150 million years ago, and what we observe today is the result of that violent encounter. frozen in time from our distant perspective as the light from that era finally reaches our instruments. Galaxy clusters are among the largest gravitationally bound structures in the universe, and when two of them collide, the encounter is not like the collision of two solid objects, but rather an interpenetration, a passing through, as the mostly empty space between galaxies allows the clusters to move through one another while their various components interact in different ways. The individual galaxies within each cluster, being relatively small and widely spaced, pass by one another like ships in the night, rarely colliding directly. But the hot gas that fills the space between galaxies in each cluster, gas heated to millions of degrees and glowing brightly in X-ray light, behaves quite differently. When the two clusters collide, their gas clouds slam into one another at tremendous speeds, and the resulting friction and pressure strip the gas away from the galaxies and slow it down dramatically, leaving it lagging behind the clusters as they continue to separate after the collision. In the year 2006, observations of the Bullet cluster by the Chandra X-ray Observatory, combined with careful gravitational lensing measurements made using visible light telescopes, revealed something quite extraordinary. The X-ray images showed the hot gas of the two clusters clearly, glowing brightly and concentrated in the region between the two separating cluster cores, exactly where one would expect it to be after being stripped and slowed by the collision. But when astronomers used a technique called weak gravitational lensing to map the distribution of total mass in the system, they found that most of the mass was not located where the gas was concentrated at all. Instead, the mass was found primarily in two separate regions, coinciding with the positions of the galaxies themselves, which had passed through the collision relatively unimpeded. The hot gas, which is the dominant form of ordinary visible matter in galaxy clusters, and which glows so brightly in X-rays that it might seem to account for most of the mass, was in fact only a small fraction of the total. The bulk of the mass had passed through the collision without slowing down significantly, without interacting with the gas or with itself, and had ended up in a completely different location from where the ordinary matter had settled. This spatial separation between the visible matter, traced by the X-ray glow of hot gas, and the total mass, traced by the gravitational lensing of background galaxies, was a profound result. It demonstrated that the missing mass in galaxy clusters could not simply be ordinary matter in some hard-to-see form, such as cold gas or faint stars or compact objects. If the missing mass were made of ordinary matter, it would have interacted with the hot gas during the collision, experiencing friction and pressure and slowing down along with it. But the lensing maps showed clearly that most of the mass had not slowed down at all, had not interacted with the gas, and had in fact behaved as though it could pass through both the gas and through itself almost completely without interaction. This is exactly the behavior expected of dark matter, a form of matter that experiences gravity and exerts gravitational influence on its surroundings, but which does not interact significantly through the electromagnetic force or the strong nuclear force, and therefore neither emits nor absorbs light and barely collides even with other dark matter particles. The astronomer Douglas Clow, who led the team that analyzed the Bullet cluster observations, described the result as direct empirical proof of the existence of dark matter, a phrase that carried considerable weight in a field where much of the evidence had previously been indirect, based on the motions of stars and gas rather than on the direct detection of where mass is located in space. The bullet cluster provided a kind of natural experiment, a cosmic laboratory in which the dark matter and the ordinary matter had been physically separated from one another by the violence of the collision, allowing astronomers to study each component independently and to confirm that they are indeed distinct substances with different properties. The ordinary matter, dominated by hot gas, had been slowed and stripped by its own interactions. The dark matter, comprising the majority of the mass, had sailed through almost unaffected, its presence revealed only by the subtle bending of light from galaxies far beyond. Since the bullet cluster observations, astronomers have studied many other galaxy clusters that show similar evidence of dark matter through gravitational lensing. The cluster known as Abell 1689, located approximately 2.2 billion light-years from Earth, has been observed extensively and serves as one of the most powerful gravitational lenses known, producing spectacular arcs and multiple images of background galaxies that allow astronomers to map the distribution of dark matter within the cluster in fine detail. These maps consistently show that the visible matter, the stars and hot gas that we can detect directly, accounts for only a small fraction of the total mass, while the rest is contributed by dark matter distributed in a vast halo surrounding and interpenetrating the cluster. Similar results have been obtained for dozens of other clusters, building a consistent picture in which dark matter is not an anomaly or an artifact of our assumptions, but a ubiquitous component of the universe that reveals itself wherever sufficient mass is concentrated. One of the most striking aspects of these observations is the experience of looking at a region of the sky that appears relatively empty, with only a scattering of faint galaxies visible, and yet finding through careful lensing analysis that this apparently empty space contains enormous amounts of massive mass, bending the light of more distant galaxies in subtle but measurable ways. The space between the visible galaxies, which seems to hold nothing but darkness when viewed directly, turns out to be filled with something that exerts gravitational influence, that curves the geometry of space-time around it, and that makes its presence known through the distorted shapes of background objects. It is a strange thing to contemplate that most of the matter in the universe is of a kind that we cannot see, that does not glow or reflect or absorb light, and that reveals itself only through the gentle bending of rays that have traveled billions of years to reach us. And yet the evidence is there, recorded in the shapes of distant galaxies, in the positions of lensed arcs and multiple images, in the separation between gas and mass in colliding clusters, and in the consistent agreement between observations and the predictions of a universe in which dark matter is real and abundant. The light that bends around nothing visible tells us that something massive lurks there, invisible yet undeniable, shaping the paths of photons and the structures of galaxies and the fate of the cosmos itself. We cannot see it directly, but we can see what it does, and from those effects we can learn what it must be. Patient observers of a universe that keeps most of itself hidden from our eyes, but cannot hide the gravity that binds it all together. In the year 1965, in the township of Homedale in the state of New Jersey, two radio astronomers named Arno Penzias and Robert Wilson were working with a large horn-shaped antenna that had originally been built for satellite communications, and they encountered a persistent problem that would not go away. A faint but unmistakable hiss of microwave radiation that seemed to come from every direction in the sky. No matter where they pointed their instrument, no matter what time of day or night they conducted their observations. And this gentle static annoyed them greatly because it interfered with the precise measurements they were trying to make. The antenna itself was a remarkable piece of engineering, shaped rather like an enormous ear trumpet lying on its side, and Penzias and Wilson had been carefully preparing it for radio astronomy work, eliminating every possible source of interference they could think of, checking every connection and every component. And still, this mysterious noise persisted at a wavelength corresponding to a temperature of just a few degrees above absolute zero. That coldest possible temperature where all molecular motion ceases, and the two scientists were quite puzzled because they could find no earthly explanation for what they were detecting. They considered the possibility that the noise was coming from their equipment, and they inspected the antenna with great thoroughness. And during this inspection, they discovered that a pair of pigeons had taken up residence inside the horn, and these birds had left behind what the scientists politely described in their technical notes as a white dielectric material, which is to say, the pigeons had made rather a mess of things. And Penzias and Wilson carefully cleaned out the antenna and relocated the pigeons to a distant location, hoping that this would solve their problem, but the mysterious hiss remained exactly as it had been before. The pigeons, as it happened, found their way back to the antenna, because pigeons are creatures of remarkable homing instinct, and the scientists had to deal with them again. But none of this made any difference to the strange radiation they were detecting. And slowly it began to dawn upon them that perhaps they were not looking at noise or interference at all, but rather at something genuinely coming from the sky, something real and cosmological in nature, something that filled the entire universe with a faint and ancient glow. At around the same time, just a short distance away at Princeton University, a group of theoretical physicists, led by Robert Dicke, had been preparing to search for precisely this kind of radiation, because they had predicted that if the universe had begun in a hot and dense state, as the Big Bang theory suggested, then there should be a remnant of that primordial heat still visible today, stretched and cooled by the expansion of space over billions of years. And when Penzias and Wilson learned of this work through a mutual colleague, the two groups realized that the annoying hiss was in fact one of the most important discoveries in the history of cosmology, the afterglow of creation itself, the light from the very beginning of time. This radiation came to be known as the cosmic microwave background, and its discovery provided powerful evidence that the universe had indeed begun in an extremely hot and dense state approximately 13.8 billion years ago, and that it had been expanding and cooling ever since. And for this discovery, Penzias and Wilson were awarded the Nobel Prize in Physics in 1978, their names forever associated with pigeon droppings and the echo of the Big Bang, which is perhaps a fitting reminder that great scientific discoveries do not always arrive in the dignified manner one might expect. To understand what the cosmic microwave background actually is, we must journey back in our minds to a time when the universe was very young indeed, when it was only about 380,000 years old, which seems like a very long time by human standards, but is really just a brief moment in cosmic terms. And at this early epoch, the universe was a very different place from the one we know today, filled with a hot plasma of charged particles, mostly protons and electrons, and this plasma was so dense and so energetic that light could not travel freely through it. In those early times, whenever a photon of light tried to move through the universe, it would almost immediately collide with a free electron and be scattered in a random direction, and then it would scatter again, and again, and again, so that light was effectively trapped, bouncing endlessly through the fog of charged particles, like a person trying to walk through a very crowded room. And for this reason, the early universe was opaque, meaning that if you could somehow have been there to witness it, you would have seen nothing at all, just a brilliant white glow in every direction with no features or details visible whatsoever. But as the universe continued to expand, it also continued to cool, because the energy of all those particles was being spread across an ever larger volume of space, and eventually the temperature dropped to about 3,000 degrees, which is still very hot by everyday standards, roughly the temperature of the surface of a red star, but cool enough for something remarkable to happen. And what happened was that the electrons, which had been racing about freely, began to slow down enough that the protons could capture them. And when a proton captures an electron, the result is a hydrogen atom, electrically neutral and quite stable. This process, which cosmologists call recombination, even though the electrons and protons had never actually been combined before, transformed the universe from a fog of charged particles into a transparent gas of neutral atoms, and suddenly light was free to travel, no longer constantly scattered by free electrons, and the photons that had been trapped for hundreds of thousands of years were released all at once, streaming outward in every direction, and those photons have been traveling through space ever since, for 13.8 billion years, growing ever more stretched and faded as the universe expands around them. The cosmic microwave background that we detect today is that ancient light, those very same photons that were released when the universe became transparent. And in the billions of years since their release, they have been stretched by the expansion of space to much longer wavelengths, shifted from the visible glow of a 3,000-degree plasma to the invisible microwaves of a radiation field with a temperature of only about 2.7 degrees above absolute zero. And this is why the cosmic microwave background appears as microwave radiation rather than visible light, because the expanding universe has redshifted it into the microwave portion of the electromagnetic spectrum. When we observe the cosmic microwave background, we are looking at the oldest light in the universe, light that has been traveling toward us for almost the entire history of cosmic time. And in a very real sense, we are seeing a baby picture of the universe, an image of what everything looked like when the cosmos was less than 400,000 years old, long before any stars or galaxies had formed, long before the Earth or the Sun existed. And this ancient light carries within it a record of conditions in the early universe, a fossil imprint of the primordial plasma that once filled all of space. When Penzias and Wilson first detected the cosmic microwave background with their horn antenna in New Jersey, they could measure only its overall temperature and its general uniformity, finding that it appeared to be the same in every direction they looked to within the precision of their instruments. And this uniformity was itself remarkable because it meant that the early universe was extraordinarily smooth and homogeneous, with matter and energy distributed very evenly across vast distances. And this observation supported the basic predictions of Big Bang cosmology and helped to establish it as the standard model of how our universe began. But scientists suspected that the cosmic microwave background could not be perfectly uniform, because if it were, then there would be no explanation for how the structures we see today, the galaxies and clusters and filaments, could ever have formed. And there had to be tiny variations in density in the early universe, small ripples and fluctuations that would later grow under the influence of gravity into the cosmic web of matter that spans the universe today. And so astronomers began searching for these tiny temperature variations, these faint ripples in the afterglow of creation. In 1989, the National Aeronautics and Space Administration launched a satellite called the Cosmic Background Explorer, known as KOB, and this spacecraft was designed to measure the cosmic microwave background with far greater precision than any ground-based instrument could achieve. And after years of careful observations and painstaking data analysis, the KOB team announced in 1992 that they had detected tiny fluctuations in the temperature of the cosmic microwave background, variations of only about 1 part in 100,000, so small that they had been completely invisible to all previous measurements. These fluctuations, appearing as slightly warmer and slightly cooler patches across the sky, were the imprints of density variations in the early universe, regions where matter was ever so slightly more concentrated or less concentrated than average. And these tiny seeds would eventually grow over billions of years into the galaxies and galaxy clusters we observe today. And the detection of these fluctuations was hailed as one of the greatest discoveries in cosmology, earning the KOB scientists John Mather and George Smoot the Nobel Prize in Physics in 2006. Following the success of KOB, astronomers launched even more sophisticated satellites to map the cosmic microwave background with ever finer detail. And in 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, known as WMAP, which orbited a special point in space about 1.5 million kilometers from Earth and spent 9 years carefully surveying the entire sky, measuring temperature variations in the cosmic microwave background with unprecedented precision. And the maps produced by WMAP revealed exquisite detail in the pattern of hot and cold spots, detail that could be analyzed mathematically to extract information about the composition and geometry of the universe. Then, in 2009, the European Space Agency launched the Planck satellite, named after the physicist Max Planck, who first understood the quantum nature of light. And Planck carried instruments even more sensitive than those on WMAP, capable of measuring temperature differences as small as a few millionths of a degree. And over 4 years of observations, Planck produced the most detailed maps of the cosmic microwave background ever made, revealing the subtle patterns of primordial fluctuations with remarkable clarity, allowing cosmologists to extract precise measurements of fundamental cosmic parameters. The patterns in the cosmic microwave background are not random, but contain a great deal of structure. And when scientists analyze these patterns mathematically, they find a series of peaks and troughs at different angular scales, rather like the harmonics of a musical instrument. And these peaks arise because the plasma of the early universe was undergoing acoustic oscillations, sound waves propagating through the primordial medium. And the pattern of these oscillations was frozen into the cosmic microwave background when the universe became transparent and the light was released. Different components of the universe affect these acoustic oscillations in different ways, and by measuring the precise heights and positions of the peaks in the cosmic microwave background power spectrum, scientists can determine how much of the universe is made of ordinary matter, how much is made of dark matter, and how much is made of dark energy, the mysterious force driving the accelerated expansion of the cosmos. And the results of these measurements have been confirmed by multiple independent observations and are now considered among the most robust findings in all of cosmology. The analysis of the cosmic microwave background reveals that ordinary matter, the atoms and molecules that make up everything we can see and touch, constitutes only about 5% of the total energy content of the universe, which is a remarkably small fraction when one considers that ordinary matter includes all the stars and planets and galaxies and gas clouds and dust grains in the entire cosmos. Everything that emits or absorbs light, everything we have ever directly observed with any telescope or instrument, dark matter, that invisible substance which does not emit or absorb light, but which exerts gravitational influence on everything around it, makes up about 27% of the universe according to the cosmic microwave background measurements, more than 5 times as much as ordinary matter. And this finding confirms and extends the evidence from galaxy rotation curves and gravitational lensing that we have discussed earlier, demonstrating that the invisible matter required to explain the motions of galaxies is also required to explain the pattern of fluctuations in the oldest light in the universe. The remaining 68% of the universe consists of dark energy, a completely mysterious component that behaves unlike either matter or radiation, causing the expansion of space to accelerate rather than decelerate, pushing galaxies apart faster and faster over cosmic time. And dark energy is in some ways even more puzzling than dark matter, because at least dark matter behaves gravitationally like normal matter, attracting other matter and clumping together, whereas dark energy seems to pervade all of space uniformly and exerts a kind of repulsive gravitational effect that has no analogue in our everyday experience. The precision of these measurements is quite remarkable, and the fact that completely independent methods all point to the same basic picture of a universe dominated by invisible components is one of the great triumphs of modern cosmology. And when we look at the cosmic microwave background, we are seeing direct evidence that the early universe, when it was less than 500,000 years old, already contained far more invisible matter than visible matter, that the seeds from which all cosmic structure would grow were shaped by the gravitational influence of dark matter as much as by ordinary atoms. And so, the echoes from the dawn of time, that faint microwave glow filling all of space, carry within them a message about the composition of everything, telling us that the universe we can see is merely a small fraction of the universe that exists, that invisible matter has been present from the very beginning, shaping the fluctuations in the primordial plasma, guiding the formation of the first structures, and continuing to this day to hold galaxies together and define the architecture of the cosmic web. As you rest and let your thoughts drift toward sleep, you may find it quietly comforting to know that the same ancient light that Penzias and Wilson first detected with their pigeon-troubled antenna is still washing gently over the Earth at this very moment, filling every corner of space with its faint and uniform glow, a remnant of the universe's earliest moments, carrying information about conditions that prevailed billions of years before our planet formed. And this light asks nothing of us, as demands no response, simply continues its eternal journey through the cosmos, a soft and patient witness to all of cosmic history. When you look up at the night sky, you see points of light scattered across the darkness, and it would be very natural to imagine that these stars and their distant cousins, the galaxies, are distributed more or less randomly through the vastness of space, like dust motes floating without pattern in a sunlit room. But this is not the case at all, and the true arrangement of matter in our universe is far more structured, far more deliberate in its architecture than our unaided eyes could ever suggest. The galaxies are not sprinkled haphazardly through the cosmos, but are instead arranged along vast filaments and sheets, like dewdrops caught on an immense and invisible web. And between these glittering strands lie enormous empty regions called voids, where almost nothing exists at all, where the darkness stretches for hundreds of millions of light years with barely a galaxy to interrupt it. This is the cosmic web, and it is the largest pattern that exists, the grandest structure in all of nature, and it owes its existence almost entirely to something we cannot see. For most of human history, we had no way of knowing that this web existed, because mapping the three-dimensional positions of galaxies requires not just observing where they appear in the sky, but also measuring how far away each one is. And that is a painstaking and time-consuming endeavor. You can photograph 1 million galaxies in a single night with a sufficiently powerful telescope, but determining the distance to each one requires measuring its spectrum, analyzing the light it emits, and calculating how much that light has been stretched by the expansion of the universe, a quantity called redshift, because the stretching moves the light toward the red end of the spectrum. Each galaxy must be observed individually, its light gathered and spread into its component wavelengths, and then carefully measured. And this takes time, a great deal of time. And so for many decades, astronomers knew the positions of galaxies on the sky, but not their distances. Like having a map that shows only 2 dimensions when you need 3. In the early 1980s, 2 astronomers at the Harvard-Smithsonian Center for Astrophysics, Margaret Geller and John Huttrer, began a systematic effort to change this situation, measuring the redshifts of thousands of galaxies in a narrow slice of the sky, working methodically through their observations night after night, building up a 3-dimensional picture of our cosmic neighborhood, one galaxy at a time. The project was called the CFA Redshift Survey, and when Geller and Huttrer finally plotted their results in 1985 and the years that followed, what emerged was startling and beautiful in its unexpectedness. The galaxies were not randomly distributed at all, but instead traced out enormous structures, walls and filaments of matter surrounding great empty bubbles. And one structure in particular stood out, a vast sheet of galaxies that came to be called the Great Wall, stretching across more than 500 million light-years of space. It was one of the largest coherent structures ever discovered, and it made clear that the universe was organized in ways that demanded explanation. The question that immediately arose was how such structures could have formed, how gravity, working patiently over billions of years, could have gathered matter into these particular patterns and not others. And the answer, when it finally emerged from careful theoretical work and detailed computer simulations, pointed directly toward the invisible scaffolding that we now call dark matter. You see, in the very early universe, just a few 100,000 years after the Big Bang, matter was distributed almost perfectly smoothly, with only the tiniest variations in density from place to place. Variations so small that they amounted to perhaps 1 part in 100,000. These minuscule differences were the seeds from which all structure would eventually grow, but they needed something to help them along, something to amplify them, and ordinary matter alone was not up to the task. The problem is that ordinary matter in the early universe was coupled to radiation, bound tightly to the intense light that filled all of space. And this coupling prevented it from clumping together under its own gravity. Every time ordinary matter tried to fall inward under gravitational attraction, the pressure of radiation pushed it back outward, and this tug-of-war continued until the universe had cooled enough for atoms to form, an event that occurred about 380,000 years after the Big Bang. Only then was ordinary matter free to begin collapsing under gravity, and by that point, a great deal of time had already passed. Time that was not wasted if you were dark matter. Dark matter, you see, does not interact with light, does not feel the pressure of radiation, does not participate in that cosmic tug-of-war. And so it was free to begin collapsing almost immediately, responding to those tiny initial density variations and slowly, inexorably, gathering itself into denser and denser regions. While ordinary matter was still trapped in its dance with radiation, dark matter was already building the scaffolding, creating the gravitational framework that would eventually guide everything else into place. By the time ordinary matter was finally released, the dark matter had already formed a vast network of filaments and nodes, a cosmic skeleton onto which the ordinary matter could fall, like rain collecting in the channels and depressions of an already existing landscape. This picture was developed through years of theoretical work and then tested in remarkable detail through computer simulations, among the most ambitious of which was the Millennium Simulation, completed in 2005 by researchers at the Max Planck Institute for Astrophysics in Germany. This simulation followed the gravitational evolution of more than 10 billion particles of dark matter, tracking their movements and interactions over the entire history of the universe, from the smooth conditions shortly after the Big Bang to the complex web of structure we observe today. The computing power required was immense, and the simulation took about a month to run on one of the most powerful supercomputers then available, but the results were worth every moment of calculation. What emerged was a detailed prediction of how the cosmic web should look, with galaxies forming along the dense filaments of dark matter and clustering especially thickly at the nodes where multiple filaments intersected. The agreement between these simulations and the observed distribution of galaxies is remarkable, and it provides some of the strongest evidence that our picture of dark matter is fundamentally correct. Without dark matter in the simulations, the structures that form look nothing like what we actually observe. The filaments are too thin, the voids are the wrong sizes, and the timing is all wrong. with galaxies forming much too late to match what our telescopes reveal. But with dark matter included, following the simple assumption that it interacts only through gravity, the simulations produce a cosmic web that matches observations in intricate detail, not just the general pattern of filaments and voids, but the statistical properties of galaxy clustering, the sizes of the largest structures, and the way these features have evolved over cosmic time. The observational evidence for this filamentary structure has only grown stronger as our surveys have become more comprehensive. The Sloan Digital Sky Survey, which began observations in 2000 and has continued in various phases ever since, has mapped the positions and distances of millions of galaxies, building up the most detailed three-dimensional map of the universe ever constructed. What it reveals is precisely what the simulations predicted: a vast cosmic web with galaxies strung along filaments like beads on innumerable strings, clustering most densely at the intersections where filaments meet, and with enormous voids between. Regions hundreds of millions of light-years across that contain almost nothing at all, just empty space and perhaps a few lonely, isolated galaxies that somehow found themselves in the cosmic wilderness. Our own galaxy, the Milky Way, sits within this web like any other galaxy, neither at the center nor at the edge. For the web has no center and no edge, but extending in all directions as far as our telescopes can see. We are part of a small group of galaxies called the Local Group, and this group is itself part of a larger structure called the Virgo supercluster. And in 2014, researchers using data on the motions of thousands of nearby galaxies discovered that even the Virgo supercluster is just a small part of a still larger structure, an immense basin of gravitational attraction containing about 100,000 galaxies spread across more than 500 million light-years of space. They named this structure Laniakea, a Hawaiian word meaning immense heaven, and it is our cosmic home, the vast neighborhood within which the Milky Way resides, itself just one filament, one strand, in the still larger web that fills all of observable space. What is remarkable about all of this, and I use the word remarkable in its quietest and most literal sense, meaning simply that it is worth remarking upon, is that the structures we can see, the galaxies and clusters and superclusters that populate our maps and fill our photographs with light, are not the primary structures at all, but are instead secondary features, tracing out a pattern that was established by something else entirely. The dark matter came first, collapsed first, built the scaffolding first, and only afterwards did the ordinary matter, the atoms and molecules that would eventually form stars and planets and people, fall into place along the framework that dark matter had prepared. When you look at a photograph of the cosmic web, with its glowing filaments of galaxies, you are seeing the ordinary matter, but you are seeing it in the shape that dark matter gave it, arranged according to a blueprint drawn in invisible ink. This is why astronomers sometimes say that dark matter is not just present in the universe, but that it built the universe, or at least built the structures within it. Without dark matter, there would not have been enough time for gravity to gather ordinary matter into galaxies, because gravity from ordinary matter alone is simply too weak, and the universe is simply too young. 13.8 billion years sounds like a very long time, and indeed it is, But it is not long enough for the gentle gravitational pull of ordinary matter to have assembled the structures we observe, starting from the smooth conditions that existed after the Big Bang. The mathematics of gravitational collapse are well understood, and when you work through the calculations, you find that ordinary matter by itself could not have formed galaxies in the time available. Not by a small margin, but by a very large one. The structures would still be diffuse clouds of gas, only beginning to condense, with no stars, no planets, no astronomers to wonder about the night sky. Dark matter solved this problem by getting a head start, by beginning to collapse while ordinary matter was still bound to radiation, and by providing the gravitational wells into which ordinary matter could later fall. The dark matter did the slow, patient work of gathering mass together, and it did this work invisibly, without emitting light, without interacting with ordinary matter except through gravity. Like an architect who designs and builds the foundation of a house and then leaves before the visible structure is added on top. By the time ordinary matter was free to participate, the hardest work had already been done. The scaffolding was already in place, and all that remained was for the ordinary matter to flow downhill, gravitationally speaking, into the waiting structures and begin the process of forming stars and galaxies. And so, when you contemplate the night sky, when you imagine the billions of galaxies strung along the filaments of the cosmic web, remember that you are seeing only the ordinary matter, the 5% of the universe that happens to glow, but that this glowing matter is arranged according to the dictates of something far more abundant, far more massive, and completely invisible. The cosmic web is really a dark matter web, and the galaxies we observe are merely highlighting its structure, like Christmas lights draped over a tree whose branches remain in shadow. The scaffolding of everything is made of something we cannot see, and yet without it, nothing that we can see would exist at all. No galaxies, no stars, no planets, and certainly no one lying quietly in the darkness, listening to these words, and drifting slowly toward sleep. And so we come to the question that has occupied physicists for nearly a century now. The gentle mystery that continues to unfold in laboratories buried deep beneath mountains and in theoretical papers filled with careful mathematics, which is simply this: what is dark matter actually made of? What are the particles or objects or phenomena that account for all this invisible mass that we have traced so thoroughly through its gravitational influence, but have never once held in our hands or captured in our instruments? And it is here, in this patient searching, that science reveals itself most clearly as a process of slow and careful elimination, of proposing and testing and revising, never rushing toward answers, but allowing the universe to reveal itself in its own unhurried time. The candidates that physicists have proposed over the decades fall into several categories, each with its own particular charm and its own set of predictions that experimenters have worked diligently to test. And perhaps the most thoroughly investigated of these candidates is a class of hypothetical particles known as weakly interacting massive particles, which physicists have abbreviated to the rather friendly acronym MIMPs. And these particles emerged naturally from theoretical frameworks that were being developed for entirely different reasons, which is often the way with physics, where the attempt to solve one puzzle frequently suggests answers to others. WIMPs arise most naturally from a theoretical framework called supersymmetry, which proposes that every known particle has a heavier partner particle that we have not yet detected, a kind of shadow family of matter that mirrors our own. And the lightest of these supersymmetric particles would be stable and would interact with ordinary matter only through the weak nuclear force and gravity, making it invisible to our telescopes and our eyes, but still capable of clumping together under gravitational attraction. And the mathematics of supersymmetry predicted that these particles would have been produced in precisely the right abundance in the early universe to account for all the dark matter we observe today, a coincidence so striking that physicists gave it a name, calling it the WIMP miracle. And this apparent miracle motivated decades of experimental searches. The basic principle behind WIMP detection is beautifully simple in concept, though extraordinarily difficult in practice, and it relies on the assumption that WIMPs, despite their reluctance to interact, must occasionally bump into ordinary atoms, transferring a tiny amount of energy that could, in principle, be detected. And because these interactions would be vanishingly rare, perhaps only a few per year, even in a large detector, the experiments must be extraordinarily sensitive and must be protected from all the other particles that might mimic a dark matter signal. One of the most sophisticated of these experiments is called Xenon 1T, and it was constructed deep beneath the Gran Sasso mountain in the Apennine range of central Italy, where 1,400 meters of rock provide shielding from the cosmic rays that constantly bombard the Earth's surface. And at the heart of this experiment sits a tank containing over 3 tons of liquid xenon, cooled to -95 degrees Celsius. And the xenon atoms wait patiently in the darkness for the exceedingly rare occasion when a WIMP might strike one of them, producing a tiny flash of light and a small release of electrons that sensitive detectors would record. And the experimenters have worked for years to reduce every possible source of background noise, purifying the xenon to remove even trace amounts of radioactive contamination, building the detector from materials selected for their exceptional purity, surrounding the entire apparatus with additional shielding, all in the hope of seeing a signal that has not yet appeared. Another remarkable experiment, called Lux Zeppelin, or LZEND for short, operates in an equally impressive location, the Sanford Underground Research Facility in the Black Hills of South Dakota in the United States. And this laboratory sits at a depth of 4,850 feet within a former gold mine called the Homestake Mine, where miners once extracted precious metal from the rock and where physicists now search for something far more elusive. And the LZEND experiment uses 10 tons of liquid xenon, making it even larger than its Italian counterpart. And it too waits in the profound silence of the deep earth, recording data month after month, analyzing every tiny signal with meticulous care. And yet, despite the extraordinary sensitivity of these experiments and the patience of the teams who operate them, no confirmed detection of a WIMP has ever been made, and the parameter space in which these particles might exist has been systematically narrowed, with each null result ruling out another range of possible masses and interaction strengths. And this absence of detection is itself a kind of result, a slow closing of doors that tells us something even as it disappoints. And physicists have not abandoned the search, but have continued to build larger and more sensitive detectors, pushing the boundaries of what is technologically possible while remaining open to the possibility that dark matter may be something other than a WIMP. Which brings us to another candidate, one with a very different character, called the axion. And this particle was first proposed in the year 1977 by two physicists named Roberto Picchi and Helen Quinn, who were not trying to explain dark matter at all, but were instead attempting to resolve a different puzzle in particle physics. A question about why certain symmetries in the equations governing the strong nuclear force are preserved in nature when there seems to be no obvious reason why they should be. And their solution to this puzzle required the existence of a new field permeating all of space, and the quantum excitations of this field would manifest as particles. Extremely light particles that would be produced in vast numbers in the early universe and would still be present today, filling space like an invisible ocean. The axion, if it exists, would have properties quite different from the WIMP being extraordinarily light rather than heavy, perhaps 1 trillion times lighter than an electron, and interacting so weakly with ordinary matter that it would pass through the entire Earth without noticing. And yet, axions would not be entirely invisible to physics, for in the presence of a strong magnetic field, an axion could occasionally convert into a photon, a particle of light, and this conversion forms the basis of the most sensitive axion searches. The Axion Dark Matter Experiment, known as ADMX, operates at the University of Washington in Seattle, and it consists of a carefully tuned resonant cavity immersed in a powerful magnetic field. And the idea is that axions passing through this apparatus would occasionally convert to microwave photons, which the sensitive detectors could pick up. And by slowly adjusting the frequency to which the cavity is tuned, the experimenters can search through the range of possible axion masses, listening for the faint signal that would indicate a conversion. And the process is painstaking, requiring months to scan even a small portion of the parameter space. But the team has continued this work for years, gradually improving their sensitivity and coverage. There are other axion experiments as well, with names like Haystack and Organ and Abracadabra, each approaching the problem from a slightly different angle, and together they represent a sustained effort to test the axion hypothesis. Though, like the WIMP searches, they have not yet produced a confirmed detection. A third candidate that has received attention in recent years is the primordial black hole, which is not a new particle at all, but rather a black hole formed not from the collapse of a dying star, but from extreme density fluctuations in the very early universe, perhaps during the first fraction of a second after the beginning, when conditions were so extreme that small regions of space could have been compressed directly into black holes. And these objects, if they exist, could have masses ranging from very small, smaller than an asteroid, to quite large, tens or hundreds of times the mass of the Sun. And they would interact with other matter only through gravity, making them effectively invisible and potentially accounting for some or all of the dark matter. Interest in primordial black holes experienced a resurgence after the year 2015, when the LIGO gravitational wave observatories made their first detections of merging black holes. And some of the black holes detected had masses that were somewhat higher than astronomers had expected from ordinary stellar evolution, leading some researchers to speculate that these might be primordial black holes that had drifted through the universe since the earliest moments, eventually finding each other and spiraling together. And while this remains a minority view, and most researchers believe the detected black holes formed from massive stars, the possibility has not been entirely ruled out, and searches continue using gravitational lensing and other techniques. And then there is an approach that departs entirely from the assumption that dark matter is made of particles or objects, and instead asks whether our understanding of gravity itself might be incomplete, whether the missing mass we infer might not be missing at all, but might instead reflect our failure to properly understand how gravity behaves at very large scales or very low accelerations. This idea was developed most thoroughly by a physicist named Mordechai Milgrom, who in 1983 proposed a modification to Newton's laws of motion that he called modified Newtonian dynamics, or MEN. And the basic idea is that at the very low accelerations experienced by stars in the outer regions of galaxies, accelerations far lower than anything we can measure in laboratories on Earth, the relationship between force and acceleration might deviate slightly from what Newton described. And Milgrom showed that with a suitable modification, one could explain the flat rotation curves of galaxies without invoking any dark matter at all. MOND has had some notable successes, particularly in predicting the rotation curves of certain types of galaxies with remarkable accuracy, sometimes fitting the data better than dark matter models that require additional parameters to be tuned. And this has earned it a dedicated following among some researchers who continue to develop and test its predictions, extending it to more complex situations and attempting to embed it within a fully relativistic framework. And yet, MOND also faces significant challenges, most notably in explaining observations of galaxy clusters and the gravitational lensing produced by the cosmic web, and the bullet cluster observation that we discussed earlier, where the gravitational lensing signal is separated from the visible hot gas, poses particular difficulties for modifications of gravity, since in these theories the gravitational field should follow the ordinary matter rather than being offset from it. And while some MEND proponents have attempted to address these issues by combining modified gravity with a smaller amount of dark matter, this reduces some of the appeal of the theory as a simpler alternative. The honest answer, the answer that any careful scientist would give after reviewing all of this evidence and all of these searches, is that we simply do not yet know what dark matter is. And this uncertainty is neither shameful nor troubling, but is rather the natural state of a science that is working at the edge of human knowledge, asking questions that may take many more decades to answer. And the experiments continue. The theorists propose new ideas. The observers gather more data. And slowly, patiently, the possibilities are narrowed. What we do know, and know with considerable confidence, is that dark matter exists, that it makes up roughly 27% of the universe's total energy content, that it shaped the formation of galaxies and clusters, that it bends light through gravitational lensing, that it left its signature in the cosmic microwave background, and that it surrounds us even now as you lie in the darkness listening to these words, streaming through your room and through your body at speeds of hundreds of kilometers per second. Billions of dark matter particles passing through you every second without leaving any trace. Let us now drift outward, together, very slowly, very gently, until we can see the full picture of what surrounds us. What holds us? what remains forever hidden from our eyes, yet present in every direction we might turn. You have been learning, in these quiet moments, about a substance that does not shine, does not reflect, does not announce itself in any way that our instruments of light can detect. And now, we shall simply rest in the understanding of what this means for the universe as a whole, for the galaxies that wheel through the darkness, for the cosmic structures that stretch across distances too vast to comprehend, and for you, yourself, lying here in the quiet, breathing softly, held by forces you cannot see. If we were to take all the matter in the universe, every particle that has mass, every fragment of substance that exerts gravitational pull on its surroundings, and if we were to sort this matter into two categories, the matter we can see and the matter we cannot, we would find something quite remarkable in its implications. Roughly 85% of all the matter in existence belongs to the invisible category. This is not a small discrepancy, not a minor correction to our understanding, but rather a fundamental reordering of how we must think about the cosmos. For every portion of ordinary matter, the atoms and molecules that make up stars and planets and comets and dust, there exist approximately 5 portions of something else entirely, something that participates in the gravitational dance of the universe while remaining utterly transparent to light. The bright galaxies we photograph with our telescopes, the glowing nebulae and radiant star clusters that populate our astronomical catalogues, these luminous objects represent only a small fraction of what is truly there. They are like scattered lanterns in an enormous darkened hall, their light revealing their own presence, but leaving the vast architecture of the room in shadow. Consider the galaxies themselves, those great islands of stars that we have come to recognize as the fundamental units of cosmic structure. Each galaxy that we observe, including our own Milky Way, is not simply a collection of stars floating freely through space. Rather, each galaxy is embedded within a much larger structure that we cannot see, a halo of dark matter that extends far beyond the visible boundaries of the stellar disk. These halos are immense beyond easy description. Our own Milky Way, the galaxy in which you currently reside, has a visible disk of stars that stretches perhaps 100,000 light-years from edge to edge, a distance already so large that light itself requires 100 millennia to traverse it. Yet, the dark matter halo that surrounds and permeates our galaxy extends much further still, reaching outward perhaps 600,000 light-years from the galactic center, possibly even more. This means that the visible portion of our galaxy, all those billions of stars whose collective light creates the pale band across the night sky that gives the Milky Way its name, this visible portion is merely a bright core nestled within an invisible sphere of dark matter, roughly 6 times larger in radius. We live not simply in a galaxy of stars, but within a vast, dark cocoon that provides the gravitational scaffolding upon which those stars are arranged. The same is true for every galaxy we observe throughout the universe. The spiral galaxies with their graceful arms, the elliptical galaxies with their smooth, luminous profiles, the irregular galaxies with their chaotic star-forming regions. All of these visible structures are embedded within dark matter halos that dwarf them in size and mass. When we look at a photograph of a distant galaxy, we are seeing only the illuminated tip of something much larger, like observing a glowing ember and remaining unaware of the vast pile of dark coals that surrounds it. The light we capture reveals the positions of stars and gas and dust, but it tells us nothing directly about the dark matter that provides most of the gravitational attraction holding the galaxy together. We must infer the presence of the dark matter through its gravitational effects, through the way it influences the motions of visible objects, through the manner in which it bends the light from more distant sources. And when we make these inferences carefully, measuring and calculating and checking our results, we find that galaxies are not simply what they appear to be. They are far more than the sum of their luminous parts. Between the galaxies, stretching across the observable universe in a pattern of breathtaking intricacy, lies the cosmic web, that great network of filaments and nodes and voids that organizes matter on the largest scales. This web, too, is predominantly dark. The filaments that connect galaxy clusters to one another, the sheets and walls of matter that surround the great empty voids. These structures are traced by visible galaxies, but composed largely of dark matter and diffuse gas. The galaxies we observe are like dewdrops caught on an invisible spider's web, their positions revealing the underlying structure while comprising only a small fraction of its total mass. If we could somehow perceive dark matter directly, if our eyes were sensitive to whatever property dark matter possesses, instead of being tuned only to electromagnetic radiation, we would see a universe transformed. The cosmic web would become visible in its full extent, a three-dimensional latticework of dark filaments threading through space, with galaxies appearing as small, bright decorations scattered along the strands. The voids between the filaments would appear truly empty, vast bubbles of relative nothingness bounded by walls of invisible substance. It would be, in some ways, like finally seeing the architecture of a building after spending your entire life aware only of the light fixtures. And now let us return, very gently, to where you are at this moment. You are lying somewhere on the surface of the Earth, a small, rocky planet orbiting an ordinary star in the outer reaches of a spiral galaxy. Above you and below you, and in every direction around you, space extends outward, filled with this invisible substance we have been discussing. Dark matter is not confined to distant regions of the cosmos. It permeates our galaxy, our solar system, the very room in which you rest, at this very moment, as you breathe in and breathe out, as your heart beats its steady rhythm, as your thoughts begin to soften toward sleep, particles of dark matter are passing through your body. Not occasionally, not rarely, but constantly, ceaselessly, in numbers almost too large to contemplate. Estimates suggest that billions of dark matter particles pass through each square centimeter of your body every single second. Billions. Every second. Through every small patch of your physical form. These particles do not stop. Do not slow down. Do not interact with the atoms that comprise your tissues and bones and organs. They pass through you as though you were not there at all, as though the matter of which you are made were as insubstantial as a ghost. You do not feel them. You cannot detect them with any biological sense. They leave no trace of their passage through your flesh. And yet, they are there. They have always been there, streaming through the earth and through every living creature upon it since the planet first formed. part of the vast dark ocean in which our visible world is merely a luminous island. There is a certain humility that comes with contemplating these facts, a gentle quieting of our assumptions about the nature of reality. For most of human history, for the long millennia during which our ancestors gazed up at the night sky and wondered about the nature of the cosmos, we assumed that what we could see was what existed. The stars were the universe, or so it seemed. The darkness between them was simply absence, emptiness, the void against which the bright points of light were displayed. Even as our instruments improved, as telescopes revealed ever more distant objects, as spectroscopy taught us the composition of stars and galaxies, we continued to assume that the visible universe was the whole universe, that the matter which emitted and reflected light was the only matter there was. This assumption was not foolish, not unreasonable given the evidence available. It was simply incomplete. And now we know better, though knowing better has brought with it a new and deeper mystery. We have discovered that we are surrounded by something we cannot see, permeated by something we cannot feel, held in place by gravitational forces arising from matter we cannot directly detect. The visible universe, for all its grandeur and complexity, is merely the bright fraction of a much larger whole. The astronomer Vera Rubin, whose careful observations of galaxy rotation helped establish the evidence for dark matter's existence, reflected on what this discovery meant for our understanding of the cosmos. In her words, "We have peered into a new world and have seen that it is more mysterious and more complex than we had imagined." There is something deeply appropriate about this statement, something that captures both the wonder and the uncertainty that accompanies our present understanding. We have indeed peered into a new world, a world in which most of reality is hidden from our sight, in which the bright galaxies and luminous structures that fill our astronomical images are merely traces of something much vaster and much darker. And this world is indeed more mysterious than we had imagined, for we still do not know what dark matter actually is, what particle or particles comprise it, what properties it possesses beyond its gravitational influence. The mystery remains, even as the evidence for dark matter's existence grows ever stronger. Yet there is also something comforting in this understanding, something reassuring about knowing that we are held by invisible forces, cradled in the gentle gravity of matter we cannot see. The dark matter halo of our galaxy extends around us like an enormous sphere of protective presence, its gravitational pull helping to hold the stars in their orbits, helping to maintain the structure that allows our solar system to exist in its present form. Without dark matter, galaxies like ours might never have formed, or might have formed very differently. The gravitational seeds that drew matter together in the early universe, allowing the first structures to condense from the primordial gas. Those seeds were planted by dark matter. The cosmic web that organizes the universe on the largest scales, that determines where galaxies form and where voids remain empty. That web was woven primarily from dark matter. In a very real sense, we owe our existence to this invisible substance, to the gravitational scaffolding it provides, to the way it gathered ordinary matter into the structures that eventually gave rise to stars and planets and life. And so you may rest peacefully, knowing that you are part of a universe far vaster than light reveals. The darkness that surrounds you is not empty, but full, not void, but substantial, not absence, but presence. You are embedded in a cosmic structure of almost unimaginable scale and complexity, a structure that is mostly hidden from your sight, yet fully present in every direction. The dark matter streams through you without ceasing, passing through your body as it passes through the earth, as it passes through the sun, as it passes through every star and planet in the galaxy. You cannot feel it, cannot see it, cannot touch it. And yet it is there. It has always been there. And it will continue to be there long after you have drifted off to sleep. Let this knowledge be a comfort to you, rather than a source of unease. The universe is more than it appears to be, far more, and you are part of its wholeness, held in its gravity, cradled in its invisible arms. The forces that shaped the galaxies, that wove the cosmic web, that drew matter together across billions of years, those same forces hold you gently now, as you breathe slowly, slowly, as your thoughts soften, as you drift peacefully toward rest. You are never alone in the cosmos, never isolated, never separated from the vast structures that surround you. You are woven into the fabric of the universe, visible and invisible alike, a small bright point of awareness embedded in something far larger and far more mysterious than we can yet comprehend. And in that embedding, in that connection to the unseen, there is a deep and abiding peace. Rest now, cradled in dark matter's gentle gravity, part of a universe that holds you even as it hides most of itself from view.